So the traditional way that inverses are taught in terms of graphing is to think again in terms of two different functions, f of x and f inverse of x. You shouldn't, but hey, that's how it's usually taught, where if we have that relationship, then if we want to graph f inverse given f, well, f inverse is always just going to be f flipped over the line y equals x. We have that nice symmetry there across the basic identity diagonal, which does illuminate a little bit there about the connection between them and what sort of things you might think about geometrically for a composition, that if we expect the composition of these two things to end up being the identity, how might that mean we should expect symmetries to appear for any other kind of composition, what we should expect in the middle of them, but that's much deeper than where we are now, and also that's giving a lot of credit to a process that, again, I don't really like that much. Because, it's fine if you think about these things in a completely abstract way, and a lot of times they'll be presented in a completely abstract way. But if you try to talk about it in a specific applied context, well, you get some more problems, just like we had in the last example. So let's say you work a job, and at that job, you make $10 an hour. So, if we let y be equal to the amount of money you make not per hour, as a function of the amount of hours you work, you have y equals 10x. Very, very easy linear function. So I'll call that f of x. And as a result, if you want to find out how many hours you'll need to work to make a certain amount of money, you just flip that. X is equal to y over 10, or f inverse of y. Very, very easy to get that inverse. And if we talk about that by flopping these variables back in, say y equals x over 10, we end up with a pretty reasonable graph which has the symmetry that it's supposed to, but look at those axes and tell me if that makes any sense at all. Because suddenly our y equals f inverse of x function tells us that you're going to be making something like $2 for 20 hours of work. That's completely wrong. The units there don't keep trying to mix these words together. It's too many compositions. These don't really match up in the way that you would hope for them to. And you kind of lose the entire application in that way. So instead, this is another reason why I think you should keep things in terms of this y goes into x relationship, because if you instead think of y giving you x values, then you can talk about graphing that first equation, that first function, y equals f of x, and saying, okay, give me an x, I'll give you a y, and that'll be the graph. Where the inverse says, okay, I'm going to treat the vertical axis as my independent variable, so give me a y. The dependent variable is now x, so if you give me a y, I'll give you an x. And that makes a lot more sense, because from here, if we talk about something like, say, f of 2 equals 20, that tells us that after 2 hours, you get $20. And down here, if you talk about f inverse of 20, you'd get 2, because $20 means you worked 2 hours. Again, this, I think, more clearly states the relationship when we're talking about invertible things. That the inverse isn't just a happy coincidence. It is specifically a thing that does the reverse of what we started with. Which is why I'm not going to give you many problems like this. Because the book expects you to really be super impressed with that symmetry. And that symmetry's fine. That symmetry's nice. It even shows you one cool property with how the compositions work. But it hides the important real-world idea of what an inverse is. So I don't think it's really worth your time. Anyway, this is all we're going to get for 2.7. Next week, we're going to move on into 2.8 to talk about some special formulas for things like distance and space away from points. But those are problems for next week. I'll see you in there.